Welcome once again to ChemSkills Podcast Suite. This is podcast number 4, and the topic of this podcast is balancing redox equations. In previous podcasts, we've seen how to balance simple equations. Redox equations are a little bit more complicated and require a specific rule set to follow. Firstly, and most importantly, we need to know when an equation is a redox equation, and so when to use the appropriate rules. So the first answer to this question would be you'll be told that it's a redox equation. So if we look at an example from the IB November 2009 paper 2, higher level question 1, the first part of the question says to deduce the balanced redox equation for this reaction. So you're told that it's a redox equation and you are asked to balance it. Secondly, if in the question permanganate or dichromate or peroxide are in the equation somewhere, then you can bet your life on the fact that it's going to be a redox equation. And so if it is, then you have to follow the rules for balancing a redox equation. Now here's another example. This is from the May 2009 IB paper, the higher level paper question, higher level paper 2, question 4. In this question you can see that the percentage of iron 2 ions in a vitamin tablet can be estimated by dissolving the tablet in dilute sulfuric acid and titrating with standard potassium manganate 7 solution, KMnO4. The fact that potassium permanganate is being used, almost certainly this is going to be a redox reaction. In the next sentence, in fact, you're told during the process iron 2 is oxidized to iron 3 and the manganate 7 ion is reduced to manganese 2. So this is an oxidation and reduction reaction, and hence you have to use the rules for balancing redox equations to balance this reaction. And the third and final approach that you'd have to take if you're still not sure whether it's a redox reaction is to assign oxidation numbers. And if the numbers of any atom changes during the reaction, then it's a redox reaction. And when we look at this example, this is from the SACE paper, 2008, paper 1, question 3. Write an equation for the reaction between chromium trioxide and the chromite ion. Now, typically you would look at this reaction and containing chromium. Chromium is a very common compound and a very common element in redox reactions. You would assume intuitively that this is going to be a redox reaction. But if you're not sure, then assign oxidation numbers. In the chromium oxide compound, chromium has an oxidation number here of +3. And the chromite ion, chromium has an oxidation number here of +3. So in the reaction, in the conversion of chromium trioxide to chromite, there is no change in oxidation number. And so the fact that there's no change in oxidation number means that this is not a redox equation. And so the next part of the question, state the nature of the element chromium that is demonstrated by the reaction above. You wouldn't say that its nature is redox. So the fact that it's reacting with hydroxide, one would assume then that hydroxide being alkali, that the chromium trioxide is acting like an acid because it's reacting with a base. So you'd answer this question by saying acidic. So now that we know how to identify whether a reaction is redox or not, the next step would be to follow the rules to balance the redox equation. Now, the simple method for balancing redox equations is called the ROHE method. R stands for balance the redox atoms. O stands for balance the oxygen atoms by adding water. H stands for balance the hydrogen atoms by adding hydrogen ions. And E stands for balance the charge by adding electrons. So these are the fundamental steps in the process. Balance the redox atoms, balance the oxygens, balance the hydrogens, balance the electrons, or add electrons. So let's have a look at an example And the example here is the reaction between sulfur dioxide and the dichromate ion to form sulfate and chromium 3. Again, containing dichromate, you can bet your life on the fact that it's a redox reaction, and it is, in this case, a redox reaction. So assuming that we know it's a redox reaction, let's proceed to the first step. The first step in this process is to split the equation into what we call the half equation. So we take the corresponding product for the sulfur dioxide, and that would be the sulfate. So the sulfur has stayed in the compound over here, which is the sulfate. So if we pull out the sulfur dioxide and pull out the sulfate, that becomes our first half equation. The second half equation follows the path of the chromium. So on the left of the equation it's in the dichromate, on the right of the equation it's in chromium 3. So we pull out the chromium bits of the equation, and that becomes our second half equation. So we've now split it into half of the overall equation. These two equations are called half equations, just looking at the path of each of the redox atoms. Now we come to the first step of the ROHE method R, which is to balance the redox atoms. Now these are the atoms that have changed their oxidation number. So you go through and assign oxidation numbers to the atoms in these half equations, and you see that sulfur here on the left has an oxidation number of +4, and sulfur on the right has an oxidation number of +6. The chromium on the left has an oxidation number of +6. The chromium on the right has an oxidation number of +3. So the sulfur and the chromium are the redox atoms. These are the atoms that have changed oxidation number. Now, to balance the redox atoms, this means that there must be the same number of sulfurs on the left as there are sulfurs on the right. And in this half equation you can see there's one sulfur on the left and one sulfur on the right. So this half equation already has balanced redox atoms. The second half equation, however, there are two chromiums on the left but only one chromium on the right. So to balance the chromiums we need to put a 2 in front of the symbol for the chromium ion. Now the redox atoms are balanced and we can proceed to the next step. Step 3, O, the O part of the ROHE method. O stands for balancing the oxygen atoms by adding water. And the first half equation you can see that there are 2 oxygen atoms on the left. On the right, however, there are 4. So the oxygen atoms are not balanced. Now we have to make sure that there's the same number of oxygen atoms on both sides of the equation. So we need another 2 on the left, but we can only get those 2 oxygen atoms by adding water. Now each water molecule only has 1 oxygen atom, so if we wanted 2 oxygen atoms we'd have to add 2 water molecules. So you plus 2 H2O to the left hand side. Now yes, I know the hydrogens have now been added and the hydrogens are not balanced in this half equation, but that's the next step. So we just follow the procedure step by step. We're only up to O now, so let's balance the oxygen atoms by adding water. First half equation done. Let's have a look at the second half equation. There are 7 oxygen atoms on the left, no oxygen atoms on the right, and so we have to add 7 water molecules to the right because 7 water molecules contain 7 oxygen atoms. So now the oxygen atoms are balanced. Balance hydrogen, H, by adding H+. So the H part of the ROHE method is to balance hydrogen atoms by adding H+. Now, the first half equation, we just added 2 water molecules to the left, and this has now brought 4 hydrogens, 2 lots of 2, 4 hydrogens on the left. There are no hydrogens on the right. So to balance the hydrogens, we can only add hydrogen ions. So on the right-hand side of this equation, we'll have to add 4 hydrogen ions. Second half equation, there are 7 water molecules, which means there are 14 hydrogen atoms over here on the right of this equation. There are no hydrogen atoms shown on the left. So to balance the hydrogen atoms, we have to add 14 H+, 14 hydrogen ions to the left. And now the hydrogen ions are balanced. So we've done the R, the O, and the H of the ROHE method. Next step is to do the E. And that is that we now have to balance charge by adding electrons. So the charges are shown here in these little red circles. So the sulfur dioxide has no charge, the water molecule has no charge, but the sulfate ion has 2 negatives, and the hydrogen ion has 1 positive. This gives us a total of 2 positives on the right-hand side. There are 2 negatives in the sulfate. There are 4 positives from the hydrogen, 2 negatives, 4 positives gives us an overall of 2 plus. And to balance that, we need to add 2 electrons to the right-hand side, because now by adding 2 negatives on the right, that has cancelled the 2 positives that we've got on the right-hand side, which now brings the right-hand side to 0, which is the same as the left-hand side. So both sides of the equation now have the same charge. In this second half equation, let's have a look at the charges. There are 2 negatives in the dichromate. There's a positive for each of the 14 hydrogens, so that's 14 positives. There are 3 positives for each of the 2 chromiums, and there's no charge in the water. So this gives us a total of 6 positives on the left. This gives us a total overall of 6 positives on the left, because there were 14 positives and 2 negatives, so that's 12 positives on the left. There were 6 positives on the right, 2 lots of 3. 12 positives, 6 positives, overall 6 positives on the left-hand side of the equation. So the left-hand side of the equation has 6 more positive charges than the right. So to make the left equal to the right, we have to drop this side of the equation by 6 positives. And we can achieve that by adding 6 electrons. So now when you tally up the total amount of charge on the left, you can see there are 2 negatives, 14 positives, so that gives us 12 positives, plus 6 negatives, that gives us 6 positives, leaves 6 positives on the left. On the right-hand side now, we can see that there are 2 lots of 3, which is 6 positives. So by adding 6 electrons to the left, we have made the left-hand side of the equation equal in charge to the right-hand side of the equation. We have balanced the charge by adding electrons. Now to get the overall equation, we've got balanced half equations, but to get the overall equation, we now have to add the 2 half equations. But we can only add the 2 half equations once the electrons in each of the half equations are equal. And then we add them together and cancel similar terms. So here are the 2 half equations again. You can see the first half equation produces 2 electrons. The second half equation consumes 6 electrons. Now, it's not possible for the second half equation to proceed from only 1 lot of the first half equation, because the second half equation requires 6 electrons. So therefore, we would need 3 lots of the first half equation to produce the 6 electrons that the second half equation requires. So we'd have to multiply this first half equation by 3. So I've put a 3 in, I've multiplied the coefficients of this equation by 3, and this now gives us 3 sulfur dioxide, so 6 waters, 3 sulfates, 12 hydrogen ions, and 6 electrons. And now that we have the 2 half equations with the same number of electrons, 6 and 6 on both sides of the half equations, we can add them together, and we add and cancel similar terms. So when we add these 2 half equations, we just carry to the bottom all of the components on the left and all of the components on the right, and then cancel out whatever appears on both sides. So first of all, obviously we would cancel electrons, because there are 6 electrons on the left, 6 electrons on the right, so they just get crossed out and they don't appear in the final equation. 1 dichromate ion is shown on the left, 3 sulfur dioxides are shown on the left. There are 14 hydrogens on the left of the second half equation, 12 hydrogens on the right of the first half equation. So that cancels out to leave us 2 hydrogens on the left. There are 6 water molecules in the first half equation, 7 water molecules on the right-hand side of the second half equation. So they cancel out to leave us 1 water molecule on the right. We carry down the chromium, 2 lots of chromium ions. We carry down the sulfate, 3 lots of sulfate. And I've already explained the water. And so by adding these 2 half equations and cancelling out similar terms on both sides of the equation, we end up with the overall equation here, showing the fully balanced and complete reaction for the redox equation between the dichromate and sulfur dioxide. Now, I hope you've understood this method. It requires a little bit of practice, and no doubt your teacher will provide you with lots of assignments, lots of exercises to enable you to practice the procedure. Once you get the hang of it, it's very, very easy to apply, but don't forget, it's the ROHE method that involves balancing the redox atoms, balancing oxygens by adding water, balancing hydrogens by adding H+, and then finally balancing charge by adding electrons, and then the two half equations are added together and cancelled. So thank you for listening. I hope you found this useful.